participants. We're about to start the last lecture of this session, and right now, what will continue is the story on physics of Josephson junctions, what you can get out of that, and the floor is yours.
Thank you. So, quick update on this stuff. I got great news today that the 3D printer, 2 oscilloscopes, and a laptop that I sent to Harvard made it there today. So we can start rebuilding some of these labs with little things, but hopefully bigger things in the future. And I asked them to put the beginning slides up so that you remember what we talked about, because I don't know. This is day 2. Probably, I imagine myself in your place. My brain would already be shutting down. But you know, you are the future, so you should persevere. So we talked about exotic Josephson effects, and one idea I wanted to convey is what I consider exotic, and hopefully you agree with me to some extent, that these current phase relationships, right, that is sort of how you can identify Josephson effect. You change the phase difference between the two superconductors, and you see what kind of supercurrent, maximum supercurrent, dissipationless current flows across the junction. And if it's not sinusoidal, it's already interesting, and then some of them are more interesting than others. For instance, you could have kind of a higher harmonic relation with, you know, it's almost sinusoidal, but it's a bit skewed, like shifted. The maximum is not at pi/2, but it's a bit off. And that's already interesting, happens in ballistic clean junctions. And there's quite a number of papers that observe that, not so much in my lectures, but that's already interesting. And then there's some really exotic ones like 4 pi Josephson effect, where periodicity was considered impossible when I was starting my PhD. And so we talked about the current phase relation, energy phase relation view of this. Energy phase relation, by the way, also useful if you want to think about superconducting qubits, because you put this kind of potential into some kind of loop or some kind of circuit, and you have different maxima and minima, and then you can define qubit states inside those. So you can solve just a Schrodinger equation. Instead of coordinate x, you'll have phase. And then the rest of the hour and a half, I talked about pi junctions, right? And the type that is induced by exchange coupling, where you split the spin up and spin down bands, and then you force the superconducting wave function, that condensate of Cooper pairs, into this real oscillating state, right? So this is just the amplitude of the wave function going up and down, and there is no phase, no rotation here, right? This is what it does, and that's because there's a cancellation between this kind of wave and this kind of wave that gives you a cosine altogether. And so I showed you some evidence that this state actually been observed already more than probably 25 years ago this year. I think 1999 was observed for the first time, and my PhD thesis was focused on proving that this is actually pi, that there is a phase shift of pi in this intermediate region in these superconductor ferromagnet superconductor junctions. And so we saw some half vortices popping up with a scanning squid microscope. We saw current phase relationship measured, extracted from these squid traces by subtracting a line, a straight line, the inductive effect, and the wiggle on top of it is the actual current phase relation of the junction. And so we saw that it goes from wiggling one way to wiggling the other way as you change temperature. Temperature is a control parameter in this beautiful junction because it's diffusive and temperature enters into the formula. And then towards the end, I pivoted to thinking about very similar physics, but then the control knob is different. Rather than exchange coupling here, we put a non-magnetic material, a normal metal, silver, gold, or graphene, or something like this. And we split the bands by this external magnetic field. And can you make a pi junction also this way? So that was a question I've been interested in for a while. And there's other people who've done experiments like this, and most of them are kind of similar concerns as my experiment. And then there's maybe one that I potentially believe that it's a pi junction. But I told you that the problem with these, should I open the door? It's pretty, bit more air. Breeze. Hope for some breeze. So the problem here is the orbital depairing effect, which suppresses. I didn't mean you don't have to come in, but. Open the door. Yeah, this is exactly what happens. You're hoping for one effect, you get a different effect. Okay, yes, so the other effect is this orbital depairing, which the practical implication of it is for any given thickness of your junction, it will roll down the critical current, the amplitude of the current phase relationship will just go down. In this example, where it's I believe a 20 nanometer thick aluminum silver film is the junction. Already at 0.1 Tesla, it's quite a bit suppressed. You could still measure maybe down to 0.2 Tesla. So you want your B pi, the temperature of the pi junction, to be at a lower field than this orbital depairing effect. The origin of the orbital depairing effect is that if you put a field through the junction, then trajectories enclose some flux, and it's controlled by the cross section of the junction, how much flux is enclosed. When you enclose a flux quantum, it starts to dephase. By the way, this is a more general effect also in big superconductors. So, something important that people compare superconductors by is a critical magnetic field. To what field can we still have superconductivity, right? And one way to calculate this field is to take the energy scale of the superconductor, the energy gap, which could be, for instance, for aluminum, it's 100 microvolts, order like 1 Kelvin. For niobium, it's order 10 Kelvin. For something like YBCO, it's 10 millivolts, 100 Kelvin order. That's the energy scale. And then you compare it to Zeeman splitting, because if the energies of the spin up and spin down are bigger, farther spaced than the gap, then you cannot hybridize them into a Cooper pair. There's just no way, right? And that's called the Pauli limit of superconductivity. Superconductivity must be destroyed if Zeeman splitting exceeds the gap. But in practice, if you calculate that field, that's usually an enormous field. So if you take G factor 2 in most metals, it will be many, many Tesla to exceed the Pauli limit. And so what kills superconductivity is also orbital depairing in most materials, in most real crystals. So you have to calculate the sort of coherence length as a kind of it gives you the area, and then you put the flux quantum through that area, and then your superconductivity is goodbye. And so in the junction, it's kind of the area of the junction in the cleaner junctions. Okay, so I went through some numbers. I naively said that graphene has no thickness, and same for nanotubes. And then we had in our possession indium arsenide wires, and then we got indium antimonide wires, where we made these junctions. This is a shadow technique that we use now. We made it in a simpler way back in 2010, 11. And we got this data. This is where we finished yesterday, if you remember. And so you can see the magnetic field versus current. And yeah, somebody also noticed that it's a bit unprocessed data. So the real zero is here, not here. It's an instrumental offset in the equipment, so it's trivial, no alarm bells here. But this is the real zero line. And so we can see current going down and then back up and then down again. And on the scale of, hundreds of millitesla, pretty large scale, where you would expect maybe to go from 0 to pi to 0, because the G factor in this material is very large. G factor is 50, 25 or 20 times more than a free electron. So you get a boost for the same field, 0.1 Tesla, compared to Crosser, that paper, you get 20 times more Zeeman energy, right? Compared to silver, for example. So that's the advantage. Another thing is that if we change a gate potential, we can change the positions of these nodes. For instance, here is between 0.2 and 0.3, here is between 0.1 and 0.2 for different gate settings, which tells you that there's some kind of electronic effect where the density of electrons perhaps controls the positions of these features. Another interesting thing is that they don't close, they don't completely go down. So maybe that's what I was looking for in my PhD when we were looking for the second order effect. So somewhere around here, the first order Josephson effect, IC times sine phi goes to 0. But what you start seeing beyond that is IC2 sine 2 phi, which is the second order effect, usually much smaller than the first order effect. And so maybe that's what we're seeing here.
Sergey,
Yeah.
could you comment, please, how it happens that a relatively very small variation of voltage makes such a difference?
Very good, very good. And that should be a kind of a flag, right? It's a concern, right? So if we are really changing Talos energy, which is connected to velocity, it's sort of how do we define it? So it's like h bar over time of travel through the junction, and that's Vf over L is the time. So L, the length of the junction is fixed, h bar is fixed. We are changing the speed of electrons traveling from one side to the other. And so to change this node by a factor of 2, you would think you need to change the speed at which electrons travel by a factor of 2. And that means you have to change the density by quite a bit as well. It can be square root 2 or something like that. But here, a relatively minor change in gate voltage, 20 millivolts, and also relative, right? On a scale of 2.7 volts, makes this big change. So this is suspicious. It's suspicious. Yeah. So that's a very good observation.
But what is the answer?
I'll tell you. Okay, so we deployed a number of tests to see if this is really a pi junction. And one of the tests was theoretical. For the theorists in the audience, I'm going to show a couple of models. This is probably the most advanced one, although it required the least from us, because anybody heard of this quant package? A couple people. So it's okay, how about time binding model? Okay, so pretty good awareness. So time binding model is an approximation of a transport through a crystal, where here you see all these balls, yellow balls, blue balls. Each ball is a site, and we assign it an on-site energy, and then the neighboring sites are connected by Hoping term. So the Hamiltonian is on-site energy plus Hoping, which is like potential energy and kinetic energy. I mean, in principle, you could make it at the atomic scale, where each site is an atom in a crystal, right? And that would be a pretty accurate model. It's still an approximation, but here in quantum transport calculations, you can see how many there is across maybe 10 sites, right? And the nanowire has about 1,000 atoms across, right? So each site is a representation of transport in this device, not corresponding to one atom, right? And so then the on-site energy and the hopping term do not correspond to the orbital in a indium or antimony atom or the sort of the band curvature, the velocity. They don't correspond to that, the coupling of the two orbitals. There are some effective parameters, but it looks like that. And so another thing this model has is the yellow atoms are superconductor layer, and it's implemented a little bit ad hoc because superconductivity is a many body effect. And this code could not handle that. And these red ones are leads, which means they are plane waves that are stitched onto this system. That's to make the calculation infinite size, because the wave function occupies the infinite space. So you have the plane waves coming in here, they're coupled into this hop, 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 hop. And then they also exchange with the superconductor. This package is available online. It's pretty well documented, and it's easy because you just need to define this geometry, and it does everything for you. It gives you the energy spectrum of your device. It calculates current for you. There are some tutorials that you can follow, and the idea is that experimentalists can do these calculations themselves. Okay, but the first one that they set up for us, the actual creators of this code, some of them were in Leiden and Delft at the time, also in Grenoble. And so we worked with them, and now we reuse this model, so I'll show it to you a couple of times throughout these lectures. And so for the nanowire, we have this Hamiltonian here, which includes, this is the kinetic energy term, or the chemical potential, right? This is the Zeeman term, this is the spin orbit term. And tau, z, tau, x, those are, what are they called? Nambu matrices. They're Nambu matrices. So they symmetrize this Hamiltonian with particles and holes, and that's what you need for superconductivity. So this one is a superconducting part with delta. So they are like spin matrices, like sigmas, sigma x, sigma y, sigma z, but they're taus, and they work in the space of particles and holes, because all the bands in superconductors are particle-hole symmetric. So, what else should I say about it? I cannot go very deep into quant, but if you have questions, I can try to answer. Yeah?
That's one question about the amount of sigma is just Pauli matrix, right?
Sigma is Pauli for x, y, z, right? So it's a vector.
Spin is Pauli matrix divided by 2, right?
Yeah, spin is sigma.
Sigma divided by 2.
By 2, yeah, but then there is, the 2 goes out, I think, because there's, yeah, what happens to 2?
There.
I think there's like 2 G will be divided by 2, something like that. I know this is correct. Okay. Right, so we try to glean some insights from this model into our data, basically, right? And this is another thing I want to say. I actually evolved to this view over the years, but there is a big temptation to exactly fit your data to a model. Right? You have a model that's very powerful, it's in principle microscopic, although you have no clue. You just put this in and type, and data comes out, right? But in principle, it's a tight binding model is microscopic. And you can tweak the parameters. You can tweak all these parameters that you see here, the spin orbit constant, the G factor, but also the hidden parameters like these tight binding parameters, right? The on-site energy and the hopping. And you can tweak disorder here in the potential. You can disorder the coupling between the different links, different sites. Until it looks like your data. And then you write in your paper, theory matches data. Yeah, or reproduces essential features, whatever that means, right? And sometimes you'll even plot theory on top of data in one panel, right? Or next to each other. And so I'm kind of moving away from this idea farther and farther. So first I said, yeah, no, we cannot superimpose. We have to put them next to each other at best. Now I try to separate them in different figures, just to show the data, experimental data, then have a discussion of that, then show the model. And at best, as an illustration of some of the features, but not, for instance, to extract parameters. This parameter alpha is a spin orbit parameter. In subsequent works, Delft people got it to a stage where they extracted it to be 100 times more than what I know it should be in these nanowires. And the mean free path of 10 microns they got in one of their simulations based on the same code, whereas the nanowire diameter is 100 nanometers. The spacing between the superconductors was 70 nanometers in that device, but they deduced from that data that the mean free path was 10 microns, so 100 times more than the available region that they looked at. Right? And so this kind of extreme case, yeah, I think that paper should be retracted, but it's not yet retracted. But that's kind of the extreme case of trusting the theory to compare to your data. Right? So then when it starts. So then you can take two avenues, right? The theory gives you a parameter that's unreasonable, or like Misha found that a small change of voltage gives you a big change in your data. Something strange like this happens, there's kind of two avenues that you can take. One is to say, well, something doesn't make sense, let me think about it a little bit longer. And the other one is, oh my God, my gate is so strong, or my spin orbit is so large, let's put it in nature. So you would be surprised how many people take the second path. Okay, so here is some of this simulation, and this is a cartoon of this model now at the higher level, nanowire, two superconductors, and transverse modes are depicted here. So it is a cartoon, so don't try to read it as like a graph. But you could, in principle, these energy levels lined up and also spin down, spin up, spin down, spin up, spin down, spin up. By the way, why spin down lower energy than spin up? I think that's not right, actually. So I think it should be the other way around. Because G factor is negative, so spin up should be lower energy.
I think they didn't bother.
Yeah, well, it's my paper. Yeah, magnetic field is this way anyways, but drawing arrows like this. Yeah, it's just a cartoon, right? Yeah, but these transverse modes are quantization in a cross-section of the nanowire, right? And by the way, cross-section is hexagonal, it's not a cylinder. And you could implement it in quant. You could define the tight binding model with a hexagonal cross-section. And so if you solve Schrodinger equation as just a cross-section, you will get some modes. And the idea is that these nanowires, only a few of these levels are occupied. So in a metal, every atom carries a mode. So in a cross-section like this, there'll be thousands of modes. But in a semiconductor, there is 1,000 times fewer electrons. Every 1,000 atom contributes a conducting electron. So the density is a lot lower, and also effective mass is very small, about 100th of an electron mass in free space, right? So in this material, electron can occupy the entire 100 nanometers of this wire and really present itself as a quantized mode in the entire cross-section. So this is why quantum code like quant is a appropriate, in principle, way to treat this problem, because electrons are light, big, de Broglie wavelength is large, the wavelength is large, mass is low, and you have just a few moles occupied. We think in these data, maybe 10, 20 moles occupied. Not one or two, we will get to that later. Okay, and so the terms in the Hamiltonian, yeah.
If the density is so low, wouldn't it mean that there is some problem with Coulomb interaction? It's not screened properly.
It's not as low for that to be a problem. So
what's the Thomas Fermi length for this?
So if we keep lowering it, yes, what will start happening is wire will break into quantum dots, right? But that's sort of below one subband regime.
So the Coulomb is sufficiently screened yet.
Yeah, sufficiently screened. That's right. And we can say it's not there, right? So in principle, but it's not part of this calculation. The electron-electron interactions are not in this calculation. They are working on I think that they already have an update where you can do it. And by the way, here's another piece of data from this paper where there is also some oscillations. The supercurrent signal is this dark color, that's the envelope. And you can see, interestingly, it goes all the way up to 2 Tesla, pretty high field. And the spacing between the contacts is about a micron. So somebody asked me, how large are these junctions, right? So this is, in 2 Tesla field, there is a tiny bit of signal for a very, very long piece of wire. Kind of impressive. I was not expecting this to be so robust. Okay, so then in the calculation, what is also nice, we cannot do that in the experiment, but we can turn on and off different terms in the Hamiltonian. So for example, we can plot what if there's only a Zeeman term present and not the others, or orbital, which is the vector potential. It's the vector potential term, so this is this interference effect, or just a spin orbit term, or a combination, or everything. And everything includes orbital, spin orbit, and Zeeman is always there. And also some disorder. So disorder is implemented by making chaos between hopping amplitudes, right, from one side to the other. And then you can calculate the effective mean-free path. Here it's still pretty clean, right? So it's 250 nanometers mean-free path. And now let's look at the left side, which is when only one single mode is occupied. So it's kind of a pure theoretical regime. Supercurrent is carried by one spin-up channel and one spin-down channel. And so the electron occupies the whole nanowire and propagates as, sort of think about a waveguide, if you, like a fiber, but for electrons. And only one mode available to transport Cooper pairs. So one interesting thing, if it's really one mode, the orbital term should be very inefficient. That's because there is nothing to interfere with. You have only one mode, and it just moves along, and it cannot make a path, a closed path. It's a purely one-dimensional quantum wire. Right? And so you can see that here, that Zeeman only, and if you add orbital, Zeeman is always on, then the two traces are almost indistinguishable. Maybe there are some numerical issues where they come apart, right? So this is a very interesting result. I'll try to come back to it later, but this will be very pure. And then if you look at the ground state phase of the current phase relation, you see that when there is this feature, it goes from 0 to pi, and then there's another lobe, and it goes back to pi. Oh, 0, sorry, it goes back to 0. So really you can have a pi junction if you have orbital and Zeeman and nothing else, and only one mode occupied. Beautiful. Now, if we have spin-orbit coupling, that's these two guys. Spin-orbit coupling makes these nodes go away. not here. They are maybe at much higher field. Why is that? Without spin orbit, we have the nodes 0, pi, 0, pretty low field, by the way, like 20 millitesla. That would be great. Okay, so spin orbit interaction, if you look at the Hamiltonian even, it's like an effective field, right? There is sigma, spin, and there is some other stuff. So it's another field that is present in the system, and it's dependent on momentum, depending on which way you move. The way it's set up is spin orbit field is perpendicular to the nanowire, and the field we're applying here is parallel to the nanowire. So the two fields are orthogonal. And imagine a spin orbit field is large, and the external field is small. Then, if you change the external field, you don't change the total field by much. You just cant it a little bit. Right? So you don't change the situation, basically. And that's why you don't achieve any Zeeman splitting. The total field is already large. But spin orbit field is a funny field because it's opposite direction for different spins. And so it doesn't lead to Zeeman splitting in the same way as the real field. So it doesn't lead to pi junction. So it splits the bands this way rather than this way. So electrons stay at the same energy and the same momentum. Should I draw it? Maybe I should use the board. I said I won't. So in the Zeeman pi junction, we have this situation. And the reason why we have oscillations of wave function is because the spin up and the spin down have different momentum. And in the spin orbit case, the bands split this way, and wherever you draw your momentum, you will have these two guys, or maybe these two guys, they have the same momentum. That's symmetric here. And if you combine Zeeman and spin orbit, you start to skew a little bit like this. This goes down, this goes up. But this effect is reduced because there is this huge splitting this way. Okay, so but of course we do have spin orbit, and so we are on one of these traces. Now, in a real wire, we have all of these things, and so what you need to look at is the red trace. The red trace here kind of looks like the data, right? It wiggles up and down, it wiggles up and down, all the way here. So you can say the model agrees with the data. But these wiggles, you can see the ground state phase here, don't really correspond to 0 to pi jumps at all. In fact, it's very interesting because the ground state phase drifts. It starts at 0 field, but then it goes not to pi, but to something, some value, and it kind of randomly moves up and down. It's not 0 and not pi, it's something in between. So that's the case of the phi junction. That's another junction, a very interesting junction too. Not the pi junction I was trying to find, right?
It's just one disorder realization.
This is just one disorder realization, yeah. But we did, what did we do? Yeah, we did a chemical potential sweep versus field, and we see sort of a lot of there. Yeah. Right, so, but again, we didn't try to fit all these wiggles to these, right? We just see sort of there's some wiggles. And you can see also here that if you remove disorder, and if you remove spin orbit effect, again, you start seeing 0, pi, 0 again. Right? So for the purple and the cyan, the blue. seems like pi junction is difficult to see. And also, these kind of data, when there is this node, or some people call it reentrance, current goes down and then back up, it doesn't mean that you went from positive current through 0 to negative. It's just this kind of orbital, essentially orbital interference effect in a mesoscopic conductor, where you have several modes occupied. And what this interference is you scatter from one mode to the other, and you kind of make a loop in this space of modes, and you enclose flux by doing that. And you have destructive and constructive interference of these wave functions. And you have this effect. But another thing you have is if you add spin orbit in the mix, you get this phi junction effect. Because that comes from spin orbit. So maybe this is interesting to chase, interesting to find the phi junction here. It would also be interesting to try to approach the pure single subband mode regime, because if in a single subband regime we see some nodes. If there's only one subband, then it cannot be interference. Cannot be interference. For interference, you need many subbands. So if we achieve one subband, maybe we see a node, maybe that's a phi junction. So yeah, here is a more detailed view, and all these curves are current phase relationships taken at different points on these traces. And these are energy phase relationships, right? So this is the same thing, just energy phase and current phase. And these traces are under different circumstances. For instance, these are no spin orbit and different chemical potential. Here, no orbital, no spin orbit. And here with disorder and everything. And so you can see some of them look pretty sinusoidal, maybe skewed a bit because it's pretty ballistic. And it goes from 0 to pi junction because it goes this way and then it goes the other way. Some of them are pretty weird, like multi-harmonic ones. And if you go to this side with everything included, you can see that the minimum is not at 0 and not at pi, but at some value in between. That would be the phi junction, right? And the corresponding current phase relation is a random wiggle, essentially. It should be impossible for Josephson effect to look like this, but it does. Right? So I puzzled a lot about how to measure this shift. Of course, you could put things in a squid and detect the phase shift like I did with the pi junction, right? I cooled down through pi transition and it shifted from 0 to pi very abruptly within 10 millikelvin. It shifted from 0 to pi. That was very clear. Now, if it's not from 0 to pi, if it's drifting along, that's much harder to make an experimental conclusion about. It's not such a dramatic effect. And also, to induce this effect, you put a parallel field on. And this field, if something is off, if you're not perfectly flat, it will also couple into the loop, and that will shift all the curves as well. So how to separate the field effect, the screening effect, from what the junction does. So this is not a trivial problem to find this green wiggle, the green wiggle. So let's talk about it. So we leave pi junction aside. We now think, well, it's really hard to find. The model says pi junction under realistic conditions is very unlikely, despite all the nodes and reentrances. Maybe we can find a phi junction. So this is, let me just explain what it is, a phi junction now. So what I want you to think about is a Josephson effect like this. It has two terms, two orders. First order term, I1 sine phi, plus some arbitrary offset phi naught, which comes from spin orbit interaction. And the second term is the second order, I2 sine 2 phi plus 2 phi naught. So everything double. Now, if that was it, if there wasn't this little component here, that would be just a sinusoidal function with two harmonics shifted by phi naught. Shifted. And I told you that this trivial shift is hard to detect because if you make a squid, there's all kinds of shifts in real experiments. Hard to detect. So comes to help this extra term if you allow a displacement between the first harmonic and the second harmonic, and especially if it's proportional to field, which also comes from spin-orbit coupling, then you can be in a situation like this, the black curve. So what is the black curve? Is the addition of the red and the blue. The red is the first term. The blue is the second term. Both are just sinusoidal functions. One is double the frequency of the other. And then if you add them up, you have this oblong curve. It's not symmetric with respect to inversion of phase. And also the amplitude on the negative side is different from the amplitude on the positive side. Question?
Yeah, what's the order of beta ds compared to phi?
Right. So what the question is, how big is beta and how big is phi naught? So this is a completely illustrative model that just kind of generates the behavior but doesn't put any numbers on it. And we do not have currently a theory to calculate this beta. So we can kind of, the best we can do is take our data from experiment, fit it, and say beta is this.
But at least any idea why this beta should exist?
No. Well, due to spin-orbit.
Why spin-orbit differentiate between first and second harmonic?
Right, so I don't know. This one,
Why if I notice the same in first and second? If there's no magnetic field.
well, if there is, phi naught is also dependent on field. Yeah.
No, it's not field on the number of. So it's the same phi naught in the first and the second.
Yeah, I mean, you can say that the phase shift in the first and the second is different, and the difference is expressed by this extra term.
And if there is no external field, then you have no phi naught.
Right, no phi naught, and yeah, so phi naught is also a function of V. Yeah, it's in a subsequent slide. Yeah, yeah. So to a large degree, the reason I don't have an answer to this question is these two guys, they are very lazy or very busy, and they do not calculate beta, even though they keep telling me that they have an idea. And I'm going to go there next in 1 week, and I will slam my fist on the table and say, when can we have the beta calculation? But you can see that at large enough field, this can actually roll over. Like this term can become large. And so it can actually change the order of the blue and red curve eventually. The difference between them can run over pi over 4 or pi over 2, and they will, the skew will change direction, basically. Yeah, maybe one of you can calculate beta. I think it's a very interesting problem. Okay, so let's look at some data then. So this is now really these kind of junctions that I introduced to you, made in my group in Pittsburgh. And what is also quite interesting is that for many years, we always applied magnetic field in this direction along the nanowire for a few reasons. One is that is actually the direction we need to make Majoranas. So you make Majoranas, try to make Majoranas for years, and that's the direction that's important. So even 10 years ago, we had similar junctions in Delft, and we just never rotated the field and to look. We even rotated it, but we didn't look at the right, like a positive and negative field and so on. So, and you can also see that z-axis is this one along the wire, and the signal, this is the supercurrent region. It survives to much larger fields, right? To 1 Tesla, it survives. And that's because the cross-section of the wire is pretty small, so you put field in this direction, and to accumulate orbital debearing, to put a flux quantum in the cross-section of the wire, takes much more field. And the other reason is this shell of superconductor is very, very thin. It's 15 nanometers thick, and along this direction, field is perfectly aligned with the shell. No matter where it lies on the wire, along this one axis, we're always looking into the film. And so to kill superconductivity in this tin, you can go to very high field. So this is a very nice regime for give a large range of field. Now in Y and X, it decays much faster. Here it's 0.3, 0.3, and that's because you're applying field this way or this way. You are first of all perpendicular to the shell, at least along some of the facets, and so you are orbitally debearing in the shell this way. You can put a flux quantum through the shell. And also, the junction itself is actually larger because this is the distance between the superconductors, but Cooper pairs, electrons in the nanowire travel in a much larger window. There's also London penetration depth effect, so the junction is actually larger this way. Okay, so we never looked at it, but now we did, and what I want you to see here is look at the X. And do you agree with me that this maximum and this minimum are misaligned a little bit? Like, it's like that. Yeah, I should have made it bigger, maybe. But this is what we call it skew, right? So it's the same data, critical current versus field, but now the field is perpendicular to the wire. It's skewed like this. So people call this diode effect. I hate this name, but that's sort of a common term. To me, this is how you can get to the phi junction. So another thing I want to point out to you here is that along the axis where spin orbit is oriented, so basically you have electrons moving along the wire this way, electric field pointing this way from the substrate. It's just the asymmetry broken by putting the wire down. And electric field cross magnetic field gives you spin orbit this way, along this axis, along the x direction. And so when you apply external field along x, you add or subtract from spin orbit field. So the fields are not perpendicular, but they are aligned. The spin orbit field is in the same direction as the Zeeman field. And so for one spin direction, you will have bigger one, for the other one you have smaller one. Then,
Sorry, are you saying that spin orbit term is due to the substrate or
yeah,
the intrinsic?
due to the sub. Well, it is. It's intrinsic. It's a Rajba term. This term is intrinsic, but you need electric field externally from some kind of broken symmetry in the device, and it's broken this way by the substrate. So just from symmetry, you can argue that it's pointing this way. And we have multiple measurements that tell you that it's always pointing this way, from kind of quantum dot states or similar triplet anti-crossing disappears when you rotate it, and things like that. Yeah. So now what happens? Why this and this are? You can see there's inverted symmetry in this plot. So what happens is, if you replace the bias direction from positive to negative and field from positive to negative, you completely flip the situation. So electron moving the other way, for the opposite spin, it would move down. Right? And the electron moving this way, for this spin, it will move down. So there is, that's why it's skewed like this. Should I draw it, or is it okay? And now what's interesting is Y is actually not so skewed. That would be also, in this framework, reasonable, because Y is again perpendicular for spin orbit. So then we're back to this physics that the two fields are orthogonal, one is large, one is small, and the vector is just scanting. It's not inverting. Okay, so now what people do is they plot the positive branch and the negative branch in the same direction. So multiply the negative branch by -1, and you can see now in the data that the maxima are separated. Then you can calculate the skew parameter and get a curve like this. So from this curve you get to this curve. And now you can rotate the field in the y-x plane, z-x plane, and the yz plane. And so whenever x is part of the equation, like your rotation here or here, the skew coefficient does something, and when you rotate it perpendicular to x in the yz plane, there is very little effect here. So this kind of indicates that the symmetry of this skewness is the same as the symmetry of the spin-orbit field. So this is sort of the most solid piece of data we have. We've seen it on 3 nanowires, and we did not see behavior that contradicts it until a year later. But there was only one graph like that, so we are not pulling this paper yet. This is for you. Okay, so now a little more detail about this model. So if you just have two-component current phase relation like this, and then you make parameters, the phenomenological parameters have these dependencies. Current in the first harmonic decays with field. Current in the second harmonic decays with field to slightly different. And then the difference between the first and the second is proportional to field. And then you calculate the total current as a function of field, and quantitatively you get this skewed pattern, right? So this is the current phase relation, this is the actual measurement. Measured current, you can see the maximum here is slightly positive, minimum here is slightly negative. And this node at 1 is completely artificial, right? It's just from this parameterization that we chose. So this is how you get from this kind of current phase relation to this. This is completely hand-wavy, not microscopic. We don't know where alpha comes from in this case. It used to be beta, in this slide it's alpha. I apologize for this. But if this is true, then from this kind of inversion symmetric data, you can prove the existence of phi junction. So this, for it to be this, there has to be this term here, these terms, right? But if the junction was purely sinusoidal, without the higher harmonic, you wouldn't be able to see any of this, right? It has to have at least one higher harmonic, maybe more. So it has to be already a pretty interesting junction, and then you can leverage that. The harmonics start to shift differently with field, and you can prove that you have a phi junction. So as opposed to pi junction induced by field, phi junction turned out to be maybe possible to prove, which is kind of interesting. Now, we also did quant model, the same model I just introduced you, right, with the tight binding calculation. It's the same junction. The only thing we have to do is now turn the field again. Not along the wire, but rotate it in different directions. And what's interesting, the model does reproduce some of these features. Again, not quantitatively, but at least qualitatively. For instance, we can reproduce in the model this type of behavior. We can reproduce anisotropy of the skew parameter, gamma. And by the way, here it's not so perfect. The data is better than the model. That's also a little bit suspicious when that happens. So there's a little bit of skew in this direction, but it could be due to this little bump here. So when we turn off spin-orbit interaction, we still have a little bit of an effect here. So that's interesting. This is due to orbital effect purely. We also have some kind of skew. And so that would be in any direction valid. So we're trying to understand this. It could have to do with some kind of chirality in the sample. This is still an open question, basically. But so there's the model may be revealing some other possibilities to get this diode effect, basically.
This is also
Yeah. This is a multi-mode disorder, but not too many modes, right?
and if you switch disorder off, then there is no. Can could you just show
I don't
me
remember.
one that is pi or disorder?
I don't remember what happens in the model if you switch it off. If I were to guess, it probably still will be there. What you mean is here, right? Here, I have to have disorder before this guy appears, right? All of these, there's no phi junction. You can see the minimum is always 0 pi, 0 pi, here maybe, but that's because it's sine 2 phi. 0 pi, 0 pi. And only with disorder, I start having this. But in these simulations, the field is along the wire. And so what happens here is, to get to the phi regime, we need enough disorder so that the electrons scatter and spend some of the time traveling sort of semi-classically perpendicular to the wire. And then spin orbit will be kind of along the wire. Spin orbit will turn with the. So we essentially, it becomes a three-dimensional junction, right? And then in all directions you will have some skew. And in this realization of the model, there is disorder, but it's maybe a little more clean, but the field is perpendicular to the wire. And so it's along the same direction as spin orbit. And so it breaks this symmetry very strongly. And so also you can extract quant will give you current phase relation like that. Give me current phase relation, and you can ask the question. Well, are there these harmonics and are there phase shifts between them? Right? What does the current phase relation look like? And the answer is basically yeah. It looks like the phenomenological model. Let me see if I have the. Oh, I removed the. I'm sorry, I removed the actual plot of current phase relations, but I have the spectrum, right? So first of all, this is harmonics, like first, second, third, and there is a sine term and a cosine term. So if there is a phase shift like this, it is also the same as having sine and cosine terms. That's trigonometry, right? And so you have the sine and cosine terms present. Which means that it's not a purely sine function, it's shifted. And there are higher harmonics, not just the first and the second, but also a little bit of the third and the fourth, etc. And by the way, also the signs alternate. Positive, negative, positive, negative, positive. And that's just from the Fourier transformation of a straight line will give you the alternating Fourier components. So, quant also indicates that the current phase relation is something like this, like the model we assumed, but only with more harmonics, the third and the fourth, etc. Again, we don't know why. We just put in the type binding code, the spin orbit, the Zeeman, the orbital, and the disorder, right? And this comes out. So there is no insight, so we wait for our friends from Grenoble to come up with the insight, or anybody who's interested in this problem. Okay, so there's also a gate voltage dependence, not very clear, like you want spin-orbit to be proportional to the electric field, so maybe with a gate you can increase spin-orbit or decrease spin-orbit. But in my experience, in these nanowires, it doesn't really work, or you have to go to very large gate voltages beyond the scale we explored here. So maybe in future work we can sort of enhance the effect by introducing gate. Okay. So this is not an entirely useless effect, the phi junction, and what is interesting about it is that the current phase relation, again, current phase relation is has odd terms. If you expand it in phi, it will have not just the phi squared from the sine or the cosine, but also the phi third. And that's because it's not the same for positive and negative, and not the same for positive and negative phase and positive and negative current. So if you do an expansion of it, you will have odd terms. And these odd terms happen to be heavily sought after in the world of qubits, of microwave circuits that work to couple qubits to amplify the signals from qubits. So there's a device called snail, which stands for superconducting something. I always forget. Non-linear. Yeah, it does. It's a the reason I don't remember it is because it doesn't abbreviate. They just thought snail was a cute word, and yeah, and it doesn't actually mean much. But it is an asymmetric squid. There's a big junction in one arm and small junctions in the other arm. And if you put a signal through it, it also gives you the same effective current phase relationship as one single phi junction. Okay? So you can already build it out of conventional components to get these third order terms. And the third order coupling between microwave signals or the amplification, if you pump it with another tone, it's more efficient than the traditional scheme which relies on fourth order, right? Just from the fact that it's one order less, it's more efficient. So the traditional schemes from circuit QED to, for instance, couple two transmones, or to build a Josephson parametric amplifier, if you ever heard these words, they rely on this fourth order scheme, which works pretty well, but it costs you more resources. And the third order one is nicer. And so here my student Tasnom has done a calculation, put in this current phase relation as a function of field, and found that there are sweet spots, certain fields where the even harmonics are zero and it's entirely odd. So in the entirely third order. So this is just plotting the current phase relation, energy phase relation in this case, as a function of field. You can see at zero field is symmetric, then it becomes asymmetric, like positive and negative branches are different color, and that's where you have a phi junction. And eventually there is a spot marked by the dashed line where the fourth order term goes to zero, the purple line, and the third order term is the dominant one. So, you know, we might explore building these devices into a microwave circuit and see the purely third order generation from a single nanowire. So it can tell us something about the spin-orbit interaction in this wire and microscopic physics in it. Who knows? Maybe it will become a useful device in some application. Okay, so I'm showing you this again. This was my plot for the model, for the nanowire, and we talked about this and how it is most likely a phi junction, not a zero junction, not a pi junction, but quite likely a phi junction, just need to prove it. And I said, oh, we found a way to prove it. If it has more than one harmonic, then it becomes skewed. These data become skewed. All you need to do is rotate the field, which took many years to do for my student to just, you know, of course, in Delft, we did have one vector magnet for the whole institute, and that was one of the first ones. And now in my lab, every fridge has a vector magnet. So any sample you put down, you can just start rotating the field. And pretty much, as soon as you rotate the field, you can write another paper on whatever you've been measuring before you start rotating the field. Like, for instance, we were measuring G factors of electrons in quantum dots, which were large in these indium arsenide, indium antimonide wires. And then you get a vector magnet, and then you write the paper G factor and isotropy. Right? So and here it's another example where you rotate the field and you find these phi shifts. But I always thought it would be very nice to go and measure supercurrent through just one mode. Really, only one channel for spin up, one channel for spin down, and see what happens. Right? So this would be this situation, and map out. Maybe what we will see is that the supercurrent decay becomes extremely long. Like for instance here, as opposed to here, there are all these nodes and wiggles at very low field, and here to half a Tesla to 1 Tesla, there is nothing happening. And maybe we'll be able to see the difference going from one mode to many modes in this very long-lived regime. Maybe we will see the pi junction at last. Maybe we'll see something else. For instance, it's very interesting to think about if you really only have one possibility to transport spin up and one possibility to transport spin down. For Cooper pair, you need both. Now, let's say Zeeman split and move one out of the energy window. And you only have one spin channel, fully spin polarized channel, connecting two superconductors. Is there still supercurrent? And what kind of supercurrent is it that is carried by the same spin channel? Yes?
Why is it important for you to find the pi junction or pi junction as they have to make, or why is it important? So like you see, you produce some graphs and you want to see a graph that will produce pi junction, right?
Right.
And why is it?
Why do we do anything? Can you name a physics goal that is more important?
Well, I mean, is there a difference between pi junction and not pi junction? Like you're trying to model a real pi junction, so you're trying to find the right model.
So okay, I can tell you about phi junction. According to me, there's been a few attempts to demonstrate it, but I am not convinced by them. Okay. So until I saw this skew, this shift in the maximum and minimum, I did not believe any claim of a phi junction from any measurement.
And in real life, in experiment, is it have to make pi junction, pi junction?
Yeah, so these are all exotic junctions, right? So most Josephson junctions that people study are just sinusoidal, like Josephson described in the 1960s. So it's just IC times sine phi, right? And all the ones I'm talking about, maybe I'm biased in your perception here, but all the ones I'm talking about are exotic. The phi junction, the sine to phi junction, the pi junction, and the topological junction are all extremely rare. In fact, when I was writing my thesis, half of them were considered not possible by the dogma of in a reviews of modern physics.
Okay.
So, I think now we have a lot of materials that are nice and clean ballistic, and so it's possible to have current phase relation that is almost sinusoidal, but a little bit skewed, like the maximum is not at pi over 2, but a little bit skewed. There are some examples of that, but to realize these kind of things, you need really to do something special, like break the symmetry with magnetic field, have spin-orbit interaction, these kind of ingredients. Right? We have very clean junctions. Now what I'm going to talk about is, can we get a supercurrent through a single mode in a true quantum wire? Those are very exotic situations. Some of them are actually very easy to visualize theoretically.
I have a related question.
Yeah.
So you said that when you see this cute picture with critical current different directions, it's an indication for the phi junction. Are there any other possible explanations for this picture?
Yeah, of course.
And second question, what is for you, what would be the ultimate proof that there is a phi junction? What you see, can you measure this phi?
Yeah, so I easier to answer the second one because I think that this measurement is as close as we're gonna get to proving it because like I said, I think if you put it in a squid, there will be this problem of straight flux coupling in and producing an arbitrary phase shift. So difficult to measure absolute phase shift. Like when I measured pi junction, it was an abrupt shift by pi, but there was also a relative shift, an arbitrary shift on top of it, right? So there was an offset and then it jumped by pi, and that was very clear, right? But if I have to rely on the offset itself, I can't tell exactly where my squid is. And the first question is, are there alternative explanations, right? So these kind of patterns are actually very easy to imagine. For instance, suppose you have a junction and the current is flowing along the junction. There is a Biot-Savart law, which tells you that there is magnetic field generated by the current. And if the current is large enough, magnetic field generated by the current can put flux into the junction and cause some interference. And then if you reverse the direction, it flows this way, magnetic field will put flux in the opposite direction. So that would be a way to get such a pattern, which is known for many decades. It's called the self-field effect.
So geometric inductance.
I guess geometric inductance, yeah. But in a junction, it's called the long junction limit when you start having Josephson vortices, essentially, in the junction. So for this specific example, you can do a calculation because the nanowire is very small and the current is not so large either. So you can calculate how much Biot-Savart field you are generating, and it's something like hundreds of nanotesla. And this shift is by tens of millitesla. So 6 orders of magnitude, 5 or 6 orders of magnitude difference. And then there's also the spin orbit direction where the effect is maximized. So from these, I think it's pretty strong. I don't say it's for sure, but I doubt we will get any closer to the phi, to the proof of phi. And yeah, it's not completely direct, like the current phasulation measurement would be better. But for instance, I don't know, complementary to this, if we can measure in the microwave the third harmonic, the third harmonic effect, the third order term, that you realize a snail, that would be sort of another proof. Okay, so now I want to talk about the single mode regime, and what we are blessed with these nanowires is indium-antimonide nanowires in particular are very, very clean. And we did see in a number of experiments quantized subband transport in these wires, known as quantum point contact. And how many of you are aware of quantum point contact? Not so many. Okay, so I unfortunately did not put a slide on that, but it's an effect where each of the transverse modes contributes the exact same conductance of 2 e squared over h per mode. So remember I told you it has a few occupied modes, like 5 or 10. Then each will contribute 2 e squared over h, and the 2 comes from spin. So each spin resolved mode will be e squared over h, and e squared over h is a conductance of about 26 kilo ohms. 2 e squared over h is 13 kilo ohms. 4 e squared over h will be 6.5 kilo ohms. And so on and so forth. And so really what you see is conductance in steps. As you open up the wire and you let it in one mode, it will be 13 kilo-ohms, or 2 is quarter range. You let it in a second mode, put more electrons in the wire, it will be 4 is quarter range, and 6 is quarter range. Now, in real samples, it's not a perfect staircase. In some very pure two-dimensional electron gas devices, you do see a very nice staircase, kind of like quantum Hall effect. You know quantum Hall effect? Quantum Hall effect is also a staircase in conductance, right? With evenly spaced steps. And this effect is very similar, except there is no protection from backscattering, so the trace can be more disordered. And especially in the nanowire, the idea is that in the middle you have this quantum point contact, and you can really tune it to the regime where there is only the first mode connecting the left and the right sides of this device. And that's a quantum point contact regime, but it is also possible for electrons to scatter from this region on the right back and change the conductance from the perfect value due to scattering. And so on top of the staircase, you get some wiggles. Okay? So that's life. And so that's what you see in the data here. This is source drain bias voltage versus gate voltage here on the gate. And the color is conductance, the IDV, in the units of 2 is quarter range. And what you look for to convince yourself that it's a quantum point contact is kind of these diamond-shaped regions of the same color. So there is dark blue, there is light blue, and there is a red bow tie here. And they are not perfect due to backscattering. But you do additional measurements to confirm that this is quantum point contact. For instance, you apply a magnetic field, and what happens is you get not 2 is quarter range steps, but 1 is quarter range steps. So spin up, spin down, spin up, spin down, spin up, spin down. So each step splits in 2. And this is what you can see here. This is the blue region widens, the light blue region shrinks. This one opens up, and the red region shrinks. And if you take a derivative of this plot, you can see the boundaries of these regions. So for example, inside this region, there is only one spin transmitting, only the spin up. And you can tell it from the value. This will be E squared over H. 1 times C squared over H. Now, not perfect, right? There's some wiggles and oscillations, but as good as it gets for a nanowire with a lot of backscattering. Questions about this? So the idea of this slide is that from several measurements, bias versus gate, field versus gate, you can convince yourself that this is a quantum point contact. And now there is also the superconductor here. So it's also a Josephson junction. So now
why wouldn't it be? I mean, it's like you put gate is present, it's always one. Why?
yeah, so it's just a practical question. Theoretically, yes. In practice, this disorder and scattering can be so large that the oscillations here are so huge that you cannot resolve how many subbands you have. Or in other words, the inter-subband scattering is so large that there is no region where you're really just transmitting through one subband. You can always scatter to another one. Right? Or there is so much back and forth and interferences caused by trajectories going back and forth that it just obfuscates your ability to resolve. And that's what happens if you're familiar with low mobility materials, that you cannot resolve the quantized modes. And certainly happens in many of these samples as well, that we cannot resolve them. And then only in a fraction we can find the evidence of these plateaus. So you look for a coincidence of two things. These kind of plateaus. I'll show you in this next slide how it actually looks for plateaus. So for instance, this is a trace at zero field. You see it's actually difficult to tell where the plateaus are from this one trace. That's because of the back and forth interferences here I drew the lines for 2 squared over h, 4 squared over h, 6 squared over h, and the blue trace kind of bounces around. Now, at 8 Tesla, it becomes a lot more organized, right? You can kind of recognize there's something here, this looks really like a plateau, maybe this one. And that's because backscattering is suppressed. You have a large field on, and it makes you travel more in one direction than in the other. There's a chiral effect. And so you always suppress backscattering by large field. Now, from 8 Tesla, we know that this is the region, definitely, where we have just the one subband, the spin up and the spin down channels only. And fortunately, in that same region, when we measure supercurrent, we have quite a bit of signal. So in this case, the 20 nanoamperes of supercurrent, pretty sharp switching. Again, there is ups and downs. It's not just a plateau. There are some interferences. But there is a signal. We can study this signal in the few subband modes. So this will be one subband. There'll be a second one here, a third. And this is also, again, it's very unusual. It's the first time that I see this happen, where this kind of strong, clear signal of supercurrent exists in such a high resistance regime with 13 kilo ohms of resistance in the junction. Usually it just gets suppressed. So you can see the quantized plateau, you measure supercurrent, and either it's not there, or it's very, very tiny and difficult to study, difficult to subject it to some additional field or gate and make something out of it. So I was quite pleased with these junctions. And so now what can we study in this regime? So great, we achieved supercurrent transfer from one mode, from one subband. We have one spin up and one spin down, and a little bit of interference. Okay, so one thing we can study is what happens when it's spin polarized. So first of all, this is what happens in fields. So this is 0 field, a little bit of field, half a Tesla, 1 Tesla, 1.5 Tesla, 2 Tesla. By 2 Tesla, it's largely gone. If you see a tiny trace here, there's a little bit of signal, but this is the kind of signal that's impossible to study, because this is just a little remnants. This one we can study, and then we do some normalization procedure and plot just the amplitude, the blue critical current or switching current amplitude, as a function of gate and field. So this will be high critical current, large amplitude of supercurrent, and this will be no supercurrent. And as you can see, as we apply field, there's a lot of interesting things happen here. There's this line where current gets pushed out. There is no supercurrent here. Unfortunately, that is the spin polarized regime. So kind of not a surprising effect. You have only one spin channel traveling between two superconductors, but you need two. You need spin up and spin down. But you only have spin up, and so you cannot actually move Cooper pairs from one side to the other. And so supercurrent goes down. Now again, we fired up the quant model to look at this. In the quant model, I guess we reduced disorder quite a bit. And so you can see these subbands. This is the orbital band, by the way. Orbital effect shifts it like this. Here the subbands cross in the model. They don't in the experiment. So the model is not identical to the experiment. And so you have these regions of fully spin polarized, both spins allowed to travel, 1.5, etc. And here there's no superconductor in this model. No blue atoms on top. Oops. And then we also extracted, here's here an experiment, we extracted the region of spin polarized from normal transport, and we did the same in the simulation. And in the simulation and an experiment, we get no supercurrent in the spin polarized regime. Unfortunately, perhaps, right? Because what if there was supercurrent here, right? In this regime where only one spin is transmitting, and we got some signal here, or some signal here. What would that mean?
They just tunnel.
Well, they're pretty far apart.
Yeah.
Right? So about 120 nanometers, and then can also try it's ballistic, so it can travel even farther. Okay, so it's a very big topic that I have not touched upon in this lecture, but many people chase triplet supercurrents and triplet superconductivity, right? The most famous example of it is Majorana is actually a triplet superconductor that generates Majoranas. And triplet means both spins are pointing in the same direction, right? So if somehow I get from my standard superconductor, this tin, just a standard metal tin, which superconductivity is singlet, like this. We know that all of these metals have the same singlet superconductivity. Then go in the wire, somehow become triplet, transport across the wire as a triplet, then flip back to singlet and go back, go through. That's what is required to enable some supercurrent here. And that would be pretty amazing, right, if that happened. Imagine what spins have to do.
We know how to do it.
Yes, tell me.
We simply need to use a superconductor which is sufficiently dissolved.
Yes.
Strongly dissolved.
Yes, so it turns out, and I don't know if I want to go into this very deeply, but it turns out that our wires are too clean, too nice to make sense. Why? Because as Cooper press tries to enter the wire, there is nothing at the interface. It's so pristine, nothing to cause the spin to flip. So what we actually need to do is put some garbage at the interface. Ideally, unpaired spins, some oxide or something like this, to allow spins to flip, and then flip back, and then maybe we will see it. So that would be the next step, right? Make worse wires. I don't know if we will still see quantum point contact, but that's what it would take. Of course, single mode transport is also interesting for Majorana. I should just mention that at least the theory papers that originally predicted Majorana, they assumed one quantum wire, one mode regime. Of course, you can also do it in the multimode, 5 minutes. Okay. I just wanted to mention that. So there is this interest in this problem as well. Now, remember another question I had was, if we have just one mode, does that mean we turned off orbital interference, and now our supercurrent can live forever, never decay? Right? Remember I told you orbital effect kills supercurrent, it's a problem, doesn't allow us to see pi junctions and all these things. Now, we are in the one subband regime. Can we now see supercurrent? Well, maybe. Some of our data is suggested that at one subband it lives longer than in many subbands, but there is also this consideration that this single subband regime is realized somewhere in between the superconductors here. Outside of this regime, underneath the superconductor, for instance, there could be many modes. And so there could be interference happening here and still suppressing supercurrent. So it's only a quantum point contact over maybe 100 nanometers or so of the wire, and not everywhere. And this is a flaw in our idea. And this is a quantum code simulation to show it. For instance, if you have really one subband in the leads and in the QPC, in the leads and in the QPC, just one quantum wire everywhere, yeah, the signal lives longer. But then if you start making more subbands in the leads, it gets suppressed. So that's why maybe that beautiful picture from the 2017 papers with a purely one subband regime is very far out of reach for us for now. Okay, couple minutes. I'll just show you this one, and we'll continue. We'll continue on Thursday with this. So there's other papers where people reported reentrances. For instance, this is in a mercury telluride quantum well, a pretty well-known paper from Harvard, and the materials are from Würzburg. And this is a planar Josephson junction, not a nanowire. It's a quantum well. It's a 2-day with 2 superconductors on top. And what this plots is resistance. So blue is 0 resistance, and yellow is non-zero resistance. And this is magnetic field, and this is some gate. So you can see they have very smoothly evolving features over large range. This is 1.5 Tesla. This is 4 Tesla. And really one line, which is a node. And there's supercurrent here, then it disappears, and then supercurrent again. And here there is a kind of a pocket separated by this line. It's very interesting data, and it is a quantum well, so it's all one mode in a planar direction, in a transverse direction of the junction, and the field is exactly parallel to this mode. So maybe these guys can achieve the pi junction. Let's leave it here. In our tradition from last lecture. Okay, thank you.